Thanks.
Thank you, Chair, for the introduction. So I'll just jump right in. So a lot of us are basically all here because we do a lot of simulations for biological tissues, and most of us do use the finite element method. A lot of biological tissues, soft tissues, are non-linear hyperelastic materials, and there has been various models being developed for different kind of tissues. For example, we've been using Ogden for skin. People use Fildaco model for artery, foam for heart valve, etc. Sometimes we want to develop our own hyperelastic material, or we're just simply trying to modify an existing material for our specific needs, which is not already in the finite element library we're using, and we have to code it by ourselves. So the procedure to do that is we first have the string energy function that fully defines material already. However, the finite element code asks for more than that. They ask for an explicit expression of both the stress tensor and the tangent modulus, which we can obtain by differentiating the strain energy function with respect to the strain tensor once to get stress and the second time to get tangent modulus. This procedure, as a lot of us know, that it's not as easy as it seems. The traditional way to implement hyperelasticity is just to get the analytical solutions and hand derive it and hand code it. The pain in there is we have to hand derive it for each form of hyperelasticity. They often appear in implicit expression of the strain tensor, like principal stretches or strain invariance. It's a very tedious procedure, and it's prone to error. For example, I'll name one example. This is an equation I took from the Abacus Theory Manual. This is one term that we're going to see. It's very long. I'm not sure whether I can get to this just correctly for the first time. And even if I get it, I'm not sure whether I can type it into my computer without making even one typo. And essentially, I need debugging to make a conversion work and accurate, and this is a very time-consuming process. So there has been past effort trying to automate this process. Young et al. In 2010, they used a symbolic toolbox within Mathematica, so they automatically derived this step using the computer, not by hand. The limitation of their method is they only make it work for one specific type of strain energy function, essentially the ones that's having explicit strain tensor term within it, like the foam. So it's only working for one type of hyperelasticity. Essentially, it's because the symbolic toolboxes nowadays are just not strong enough to do implicit differentiation. So to make it more universal, numerical methods have been tried. So me, 1996, Song et al., they use numerical differentiations to get the tangent modulus. What they did is they say if we have the stress tensor, we're going to perturb the strain tensor. So we can have a difference in stress tensor, so we can see the tangent modulus. So essentially, we're doing numerical operations on the black box of stress tensor, so it works for arbitrary material, which is nice. I think the limitation is that we still have to go from the strain energy function to the stress tensor by ourselves by hand. So I've been calling it a semi-automatic process. So what I'm proposing today is we are trying to do a step from here to here, from the strain energy function to the stress tensor, so we can use the old algorithm to go to the tangent modulus again, so we can have a fully automatic process from the first to the whole implementation. So that's the proposed method. So to do that, we've identified 3 research tasks. One is we want to develop the algorithm to do it. So essentially, we want to perturb the strain energy function psi by perturbing this strain tensor and get a difference in strain energy function. The ratio between the two is going to be the derivative, which is the stress tensor. And then we will use the algorithm developed by me in 1996 and Sung in 2008 to finish the whole the full circle. And after that, we want to explore this algorithm's perturbation parameter space. The reason to do that is this step size, like how much we're perturbing, is crucial. If we're doing too small a perturbation, then the effect is going to be small enough to be rounded off by the machine, so we're going to have a round-off error. If it's too large, then this numerical differentiation is going to have accuracy issue. So we're going to explore that. Third is, after we know what perturbation parameter works, what algorithm works, we're going to plug it in and run the finite element models to see whether it really works. So let's see the first task. So we started from the linearized form that the change in strain energy function is a contraction product between the second Gauss stress times the perturbation of the strain tensor. So we would like to construct a form of perturbation so that we can get a nice scalar product that the change in the strain energy function is a component of the second Gauss stress times a small perturbation parameter for stress, or just a step size, we can think of it. So we choose the perturbation on deformation gradient that's in this form, the inverse transpose of the deformation gradient times the Cartesian basis. So we can get a form of the perturbation of the strain tensor like this. We plug it back in. We can get the perturbation on the strain energy is a scalar product of the step size times the component of the second Gauss stress. So we get the second Gauss stress, easily calculated by using the ratio between the difference in strain energy function and the step size we're using. And for example, we're using abacus, so it asks for the Cauchy stress. To get that, we just do a push forward operation to get it in the current configuration. So that's the algorithm. We tested it using this one-term Neohooking material, which was essentially the simplest form of hyperelasticity. We directly specify the deformation gradient, so no finite element involved yet. We compared the result between the traditional analytical solution and the numerical solution, and we tried 3 different loading conditions: uniaxial tension and compression, biaxial tension, and simple shear. So the 3 columns here stand for uniaxial, biaxial, and simple shear. So we can see the x-axis is the principal stretch, y-axis is the responsive stress. The dots are the accurate analytic solution, and the lines are just numerical solutions. We can see that the line is fitting right perfectly with the numerical solution. So on a rough look, we think this algorithm works. So we finish the first step. We get this algorithm working, and we can serialize it with this previous algorithm and get the whole algorithm to run automatically. And now the second task. We want to explore this algorithm's perturbation parameter space. So we first do it for, so there are 2 perturbation parameters actually for us to see. We first look at the first one, I call it epsilon s, which is the perturbation parameter to get the stress. Essentially the step size over here when we're perturbing the strain energy function. So we have seen these 3 plots just 2 slides ago. I'm thinking that we are fitting this analytical solution with the numerical solution. So we have an r² value of it. So if we use 1 minus r² value, plot it on the y-axis, otherwise known as the residual sum of squares divided by the total sum of squares, which essentially characterizes the amount of error of this algorithm, plot it in log scale. And on the x-axis, we tried 16 values from 10 to the minus first to 10 to the minus 16th for the amount of perturbation. We see that the error first decreases and then increases again for all 3 cases. So what I did is I draw a line at 10 to the minus 4th because we think this is a really low error, which means a good accuracy. This perturbation parameter can move nicely within the wide range of 10 to the minus 4th, 10 to the minus 12th, and we all get a very good result. So that's safe, and we have a retrospective work. Next is we're going to look at the perturbation parameter that we perturb with stress, so we can get a tangent modulus. The point in here I want to make is we cannot look at this step size individually, because when we are perturbing the stress tensor is actually obtained by using this perturbation parameter in the first step. So we have to look at these 2 parameters together as they're coupled. So here's how we did it. On the x-axis, we tried also 16 values for the perturbation parameter of the tangent modulus. On the y-axis, we tried 16 perturbation parameters for the stress. We still say 10 to the minus 4th is a good accuracy, so we have this nice triangle area that we see we are having good accuracy for the tangent modulus, so the algorithm can converge. And this is the same for all 3 cases. So as long as the parameters are within this range, we're safe. And specifically, we notice that there is the same point for all 3 cases that we get the best result for. We get the best accuracy for the tangent modulus. So that's what we're going to use for our validation experiment. So we finished our second step, exploring the perturbation parameter space. We try to validate it. We coded this algorithm using the abacus, using user-defined material or UMAX subroutine, we use perturbation parameter that we just obtained in the second research task. And we used the same neo-Hookean material like the last step, and the same setup, which means uniaxial compression, uniaxial tension, biaxial tension, and the simple shear. So we are looking at two things. One is the number of equilibrium iterations it takes from the numerical algorithm versus the analytic algorithm. This is essentially an indicator for how fast this model can converge due to the accuracy of the tension modulus. We see that it's taking one more step or two more steps for the uniaxial cases, same amount of iterations in biaxial case and simple shear case. So we are converging well comparatively. And also we are looking at the relative error for the stress, that we are on the order of 10 to the minus fifths. So we are accurate, at least here in the single element cases. So after we do that, I think it works. We try the full model, which with an artery inflation using following Zulager et al. In 2004 and Sung et al. 2008. So we use Hosafel anisotropic model with two families of fibers. It's a 3D quarter model with 728 nodes and 450 brick elements. So it's actually a full circle, which is an intersection of the artery. What we're doing is we're trying to add pressure. This is unformed. We're adding pressure from within. So we'll expand and the radius will increase to this deformed state. What we're trying to observe is the relationship between the pressure we applied on the x-axis here and the change of outer radius on the y-axis here. So we see that both analytical and numerical method matches well with the experiment dots, and actually more importantly for us, the numerical algorithm is totally overlapping with this analytical algorithm. It's essentially the same because at the maximum point, the radius error is 4 times 10 to the minus 6, so it's very small. We also looked at the maximum principal stress that's distributed along the thickness of the artery wall, that within here we're having high stress. On the outer radius we have a low stress. So at different pressure levels, this distribution predicted by the finite element model from the numerical algorithm and the analytical algorithm are essentially identical. We also look at the performance of this. So the CPU time for analytical model is 3.8 seconds, for numerical model is 4.2 seconds. So you might have already noticed we are essentially using the numerical algorithm to do a trade-off between human and CPU time. We save the coding time, but of course the analytical solution that's accurate will run faster. So for this small and medium scale model, we think it's totally acceptable and good. For large model of tens or hundreds of thousands of elements, this might not really scale up. So here is how we think we should use it. For simple models, where we are still trying a lot of different hyperelastic models, time is much more expensive than CPU time because we're spending a lot of time in doing coding and derivation. In those cases, we can use this numerical implementation directly just to save time. And it's acceptable difference. For very large models, the performance is critical. If a model takes 10 days to run, essentially the CPU time becomes human time because we have to wait for this model to finish running. In those cases, analytical method should be used because the performance is critical. Still, when I'm doing those, I still find this numerical method crazily useful because when I'm deriving, I can always see the intermediate results from the numerical solution, so I can look at each component of, for example, tension modulus and the stress to make sure that I have intermediate results for debugging, and that just greatly accelerates the process. For future models, I think, if in the future there is a model with no analytical solution available, this algorithm can make that useful because we're still able to evaluate that. So I think we're opening a door with this slide. So here's the summary. We noticed that the manual implementation of the hyperelasticity is very time-consuming, so we developed a fully automated implementation of hyperelasticity. We do that by preserving the strain energy function numerically so we can get stress and tension modulus to feed into the finite element code. This tool may be used directly for quick validation, or it may be used to help debugging during the analytical implementation and derivation process. we identify the viable perturbation parameter space, and we use that to validate this tool with finite element models, with having high accuracy and having good convergence performance. A future work is we notice that there's a limitation of this numerical differentiation for various depth strain energy functions because due to the nature of the numerical differentiation method. So we are planning to use adaptive step size to deal with this problem. That's future work. Yeah. So that's all I have. I'll be happy to take any questions.
Thank you for your presentation. Question? First?
Yeah, very well, thank you. I'm thinking maybe the trade-off between the numerical time and the analytic compute time would depend on the complexity of the model itself. Any comments about that or observations?
Just to make sure I get the question
right.
right.
So you had a particular
slide for that.
Yeah, exactly. So 3.8 seconds for the analytic and 4.2 seconds for the numerical. That's for a particular material. I'm just wondering, as the complexity of the material changes or becomes more complicated, how those time trade-offs vary.
Thank you. I was thinking, when I say this scaling up, I was more thinking about the number of elements because it increases non-linearly. It's increasing non-linearly. For the complexity of the material, I think it will not increase the cost as much because the numerical evaluation it's a black box. We just plug in the value to get the perturbation parameter, even if the expression for the stress is crazy complicated.
Yeah.
The numerical black box won't be impacted that much.
Right. That's what I'm thinking actually, the numerical method will be more efficient the more terms and things you have in your hyperelastic model.
Yeah, I agree. Thank you.
Second question, sir.
Bypassing the, you're using algorithms, correct? Mm-hmm. So, you understand correctly that you are bypassing the user subroutine step, and you are feeding directly the numerical values of the tensor. I didn't get it.
Yeah, it's a good point. I didn't go into details for the how I implement it. So I didn't bypass. I just use the user material. So what people are supposed to do is the abacus feeding the deformation, and in the user material we just spit back the stress tensor and the tension modulus. So here I do the same thing. It's just the algorithm is the UMAT code will itself perturb the deformation gradient and get the stress tensor rather than go into it directly using analytical method. So we are using UMAT, not bypassing it.
I didn't quite follow. Are you doing the perturbation and the calculation in real time for every gas point of every element? So so you're effectively doing it twice. Then you're calculating the stress twice each time and seeing what the difference is. So that would explain why it's slow. But could you not do it in advance and have a look-up table or something and make it go much, much faster, especially if you had a complicated model?
I think that's a good idea. I haven't thought about that before to have a look-up table. I think that's an interesting idea. Intuitively, it's a tensor, so doing a lookup table for the tensor is something I've never done, but I think that's a good idea. I can try.
The stress is going to be easier, isn't it? I mean, the stiffness tensor is going to be a very big lookup table with lots of dimensions to it. But if you could have a good way of interpolating it, you think that would be able to run much, much faster, doing, especially with a complicated model with lots of square roots and divisions.
Right. That's right. I think that'll work.
No other question or comments? Thank you.